The difference again in the 85 and the 95 is, first of all, we have 85 and the 65 is the fan assist, of course. Principal item on that, and you can see that happens to be located up on the top on this one over here. Coupled with the fan assist, you'll always see a pressure switch. Now this switch will be mounted in the furnace, and this one, it happens to be, let's see how I can do it, right up at that location there. And what this does is it tells the main, it's got a set of contacts in it. It's just a switch that is normally open. And when the combustion blower comes on, the fan assist comes on, it creates a negative pressure inside the heat exchanger. It's drawing air and fuel mix into the heat exchanger. What we do is we connect a tube from this pressure switch to the inside of the heat exchanger, and as that fan comes up to speed and creates a negative pressure in there, that negative pressure draws against this opening here, and it closes a little switch. And what it does, it tells the furnace, the gas valve, that yep, our combustion blower is running, the fan is on, and it's okay to fire up the gas valve. So that's the second major component in a fan assist or 85% furnace. Now this furnace doesn't have a mechanical limit switch like this, which causes something to rotate and actually close a switch. It's got this kind of a limit switch in it. Here's two of them. This is a two-prong, normally open, normally closed switch. That means that there's always energy or a complete circuit through this switch at these two. So this is wired in series with our gas valve. You can see on this one, it's located right here on this furnace. If for any reason we have a blower failure or some reason that heat exchanger overheats, this little heat sensor over here, we call this a snap disc. This little snap disc will overheat, and it will pop and it will open up the connector on this circuit. Here's a second one. This is an auxiliary switch. A lot of these furnaces will have 2 or 3 or maybe even 4 of these types of limit controls at different locations on the furnace. This one looks like it's an insertion inside a heat exchanger. This is the limit switch that we see up here. We'll also see these little types of switches at different places along, maybe along the burner rack over here. So that if for some reason there's an obstruction or something in the system and it's not picked up by the pressure switch on the fan assist, and the flame starts backing up out of this furnace, it'll trip that switch as well. So we might have 2 or 3 or even 4 of these located at different places on the furnace. One over here, we may have one somewhere else on the lower part of the heat exchanger, one on the burner shield out here. That switch, we call it a rollout switch or a spill switch. In case the products of combustion, the natural gas that's being fired, if it rolls out of that burner compartment, or if it spills out of the burner compartment for some reason, it'll hit that switch and it'll shut down the blower as well, so we don't get a fire or a severe upset condition. So we got a couple of other items on these newer furnaces. We have the snap disc limits. We have the pressure control, the fan assist. We also have an integrated circuit board here that does all of the, it's a computer that runs our furnace for us. Some of these, usually when we get into the higher efficiencies, but even some of the 80–85% furnaces have multiple stage gas valves. So they'll fire at a high fire or a low fire. They might turn the blower from a medium low to a medium high if we go to a high fire or a low fire. It might adjust the blower output depending upon how much gas we're using, how much we're firing that furnace. So these integrated circuit boards do a lot of different things for us. They'll also have a location on this board where you can change the blower speeds. Now most of the supply blowers, the blower motor that delivers air to the house in a direct drive furnace, they'll be multi-speed blowers. Minimum, they're always at least 2-speed. I've seen them as much as 5 speeds. But the circuit board in here usually gives you 2 speeds to play with. There'll be one for cooling mode, one for heating mode. And depending upon which winding in that blower motor, you can select what those speeds might be. Now here in Denver, I almost always put everything on high speed because it's just tough to get, we're at altitude here, we have thinner air, and it takes a little bit more to get heat and cooling into a space. But you can select maybe high speed for cooling and medium low speed for heating. You don't need nearly as much air for heating that you do for cooling. And the reason is that when we're heating a space, if the space temperature is typically in the 68 to 72 degree range, the temperature coming out of that furnace might be 120 or 130 degrees. So we've got a 40, 50 degree temperature differential between the actual space temperature and the actual temperature of the air that we're delivering to this space. In cooling mode, we have a much narrower range. If it's 72 or 74 degrees in the space, we may only be getting 55 or 58 degree air out of the furnace. The differential is only 16, 18, 20 degrees. We need more air to pick up a thermal load because the disparity in temperatures are so much closer. So we need more air for cooling than we need for heating. So we can select that by taking one of the blower motor leads, and they're typically color-coded. Black is almost always, and I've never seen one that wasn't, but can't swear on everything, but black is almost always high speed. Red is almost always low speed. You might have a blue and a yellow or a brown. Typically brown is the capacitor on the system. And here's a start capacitor that is on a blower system. And typically brown or purple goes to the capacitor and back to the blower motor to get the blower motor started up. But typically black high speed, blue medium high speed, yellow medium low speed, red low speed. Typically 4-speed motors. Some are only 3, some are 5, but you'll almost always see the black lead parked on the cooling terminal on this board. And they'll be labeled. The board will label where you see the blower motor leads come in. You can follow them right from the blower motor to the wiring harness over to wherever it ties in on the board. And it'll mark cool and heat. And so typically you'll see the black one over here on cool and maybe the yellow one on heat. And then the other two are either parked on spare terminals on the board that don't connect to anything, or they're wrapped with electrical tape or something so that they don't inadvertently short out on something, because there's always induced current through those things. So let's see, did we cover everything? I think we've got it on our intermediate efficiency furnace. This is another pictorial, same type of thing. Our combustion blower, pressure switch, our burner compartment, the integrated board. This happens to have a different type of heat exchanger in it. We'll talk about that later on in the presentation. I think that's it for that. Let's see if there's any other missing parts that I didn't talk about. Not yet. All right, so Ken, this is a next generation furnace. This is a 80 to 85% efficient. All the manufacturers test a little bit differently on it, but they're in that 80% efficiency range. This is quite a bit different from our other furnace. It's got a whole lot more stuff on it. It's got solid state circuitry on it. Still has some manual relays and stuff, but primarily it's got 2 distinct functions that give it its much higher annual fuel efficiency rating. An annual fuel efficiency rating means that over the whole 1 year of operation of this furnace, it's going to give you better efficiency. And primarily, the first feature that we see on it that everyone becomes immediately aware of is the combustion blower motor, or inducer blower motor. This particular furnace draws air through the heat exchanger and exhausts it up through the top under a very slight positive pressure. So the combustion chamber itself is drawn down to a negative pressure, and that draws the flame into the compartment. And then the flame can be delivered in a serpentine fashion or through a series of tubes, and I'll show you some of those later. But that's the primary difference, is the combustion blower motor, and secondarily is the fact that we've got an intermittent pilot. We don't use a standing pilot light any longer. This is an electronic igniter over here, and you can't quite see it in this, and in fact this furnace isn't gas piped, so I suspect that there's a defect in the furnace itself and the school hasn't piped it in place, but we can at least show you how the sequence of operation works on it. So when we go to get a call for heat on a furnace like this, the first thing that'll happen is the combustion blower motor will come on. And that draws air through the heat exchanger and exhausts it up through the top, which will be vented up through the roof. And that's for the purpose of purging the heat exchanger, so that there's no residual gas left over inside there that might cause an explosion on the initial startup. Typically, this solid state board will bring this combustion blower motor on for some predetermined time period, 20 seconds, 30 seconds, and some of them are adjustable, so you can set those up wherever you want. And then after we go through the purge cycle, the igniter circuit will come on, and it'll open up the pilot gas valve over through here, and this safety valve is the pilot line over here. Comes down into the pilot valve over here with the electronic igniter right next to it, and then the pilot will come on and we'll initiate a pilot flame. Once the pilot flame is initiated, there's a flame sensor, which is a safety control. It's this device here, and that tells the main gas valve that we've got a good pilot and we're ready to open up that gas valve. So those are the primary features of an 85% furnace: intermittent pilot, inducer blower motor. And just as an aside, there are a handful of furnaces out there that are forced draft, where they have the combustion blower motor on a sealed heat exchanger that pressurizes the heat exchanger. And so air is being forced in instead of forced out and drawn in. That's just a slight different variation on the theme.
So that's a sealed burner chamber?
That's correct. And that would be a forced draft combustion furnace rather than an induced draft.
So it's pushing air through rather than pulling air through.
One other thing that's a little bit different on this furnace is this type of burner that we have. On the old 65%, we had the old-fashioned ribbon type burners, and there's a rack of ribbons right behind you there. I can show you that. On the one that we had just looked at before, we had big air adjusters on the front. This one has air adjusters over here. They're all missing here, but it's a kind of a cylinder that goes around here, and you can rotate it through an opening and bring the air in through the different burner orifices at this location. Then the gas is injected here, and the flame rides on this ribbon type burner over here.
So the adjustment would partially cover this opening right here.
It's like a little cylinder with two holes in it, and you can rotate it so that the holes are either blocked off by this or they're rotated around, and you can adjust the individual burners with those. It's an old-fashioned ribbon burner.
These are actually perforations.
That's correct. The little slots in the top of that steel tube, and that's what allows our flame to come out. And then the flame, of course, rises up through the heat exchanger. This newer furnace, we can set that down. This newer furnace has a different style of burner. It's called an in-shot burner. And basically what it does, it injects gas at the inlet port over here, blows it through this nozzle, and then the nozzle blows the gas with the primary air that's coming out through here into the heat exchanger, and carries it up through a tubular, a series of tubes inside there, and then we blow our air across the outside of those tubes.
Why the gap between the initial tube and the burner tube?
That's to allow excess air to enter the combustion compartment. That's because we have all of this air we're inducing through this blower. We need to get a good shot of air in through that burner assembly, And so we have that gap there, and we actually draw the flame into the heat exchanger.
Gotcha.
So we can go ahead and cycle this on. Again, we don't have gas hooked up, so we're not going to get ignition on it, but at least you'll be able to see the combustion blower, the sequence. Combustion blower first, then we get ignition at our spark, we get flame sensing at the pilot light, and we get the main valve opening. And I'm sorry that I can't provide that vision for you today. I want to show you one other safety feature, but let's try and run this through the cycle first. What I had to do in this case was just put a jumper on here because this furnace isn't ready to go. So I jumped out where the thermostat would normally be. The red lead comes off of here, and that's power from our thermostat, goes up to our thermostat in our house. The thermostat switch makes and brings power back down to the W terminal on the circuit board, which is going to bring our primary call for heat. So we've got power at the furnace here. We've got it plugged in over there. And we'll go ahead and close the door. There you go. Boy, that's a terrible sounding combustion blower motor. That thing's about ready to fail. It's got a bearing problem, a sleeve bearing problem, or just worn out. That's something I would be looking at as a furnace inspector. We've got an older style furnace here with a bad or an imminent failure in the combustion blower motor. One other safety feature I wanted to point out to you on this furnace is that this inducer is drawing a negative pressure through this heat exchanger. And in order to also enable the gas valve to open or the pilot valve to open, we want to prove that there's negative pressure inside this system. So this device here is a pressure switch. And it's got a tube that comes from the inside of the switch, and it's set up on a little opening in the heat exchanger there. So this tube on this pressure tap is sensing negative pressure inside that heat exchanger as this blower is inducing that negative pressure, and it's closing this switch over here. Once this switch closes, that enables the gas circuit. This orange lead is the gas safety circuit. Comes out over here, goes up through a gas safety limit switch at this point here, runs back down to the gas valve, goes through another safety limit. Here's another safety limit switch over here, and eventually goes to the gas valve and completes that gas circuit. So this safety could shut down the system, the pressure could shut down the system, this limit switch could shut down the system. All three of these are safety controls on this induced draft 80% furnace. I'll shut that down for a second. I did want to show you one more thing. And that is, we looked at that limit switch on that other furnace. That turned on the fan, and it turned on the, and it maintained the gas pressure on this. I'm sorry.
Safety, yeah.
Right. This one has a different style. It's called a snap disc. This is a little element over here that if it gets overheated, it will cause this little disc inside to snap open. It's like an old-fashioned clicker type thing.
Break the circuit?
Breaks the circuit, shuts down that gas valve as a safety. We have the same type of switch right up in here. This is on the exhaust side of the combustion blower motor. If for some reason the exhaust gas temperature got way too high, that would shut down the gas valve as well. So those are the two safeties. Now, oh, go ahead.
Okay, where's the high and low limit? Because that's a safety and that's a safety. But
Well, these are both limit switches. So they're high limit switches, and they shut down the gas valve. The question, of course, is what turns on the blower? We don't have that combination fan limit switch anymore. Well, the blower is activated through the solid state controller down here. A lot of these have dip switches on them where you can set the blower delay, the delay on and the delay off. And so once this system is up online, we got the pilot, we got the gas valve open, we got gas flowing, we got combustion, then we go into a time cycle.
Right.
And we turn the blower on based upon a predetermined time interval. Could be 30 seconds, could be 180 seconds. And then once the system is satisfied, our thermostat is satisfied, we're not calling for heat anymore, the gas valve, the gas train will shut down completely. and then we'll go into a cool down cycle, and the blower will remain running for some predetermined set point as well.
So it sounds like over just the operational things that you've talked about in the last few minutes, there really isn't a lot that inspectors are going to actually see that they're going to call out as a problem. More, it'll be a failure of the system to respond to the call for heat.
Yeah, pretty much. Now, the one thing that's kind of nice about these systems, though, is that you can simulate a limit switch, a limit failure on the system. You can just take one of these wires here, pull it right off. At that point, you should see those main burners go right down. If there's something wrong, there's a defect in either the combustion blower or any of these other switches, if for some reason that gas valve stays open, you've got a real problem with your gas valve. It's a serious safety problem.
I'm wondering, the reasons I can think of for an inspector not to do that is that if this is old and he pulls that off and the whole thing falls apart, they don't carry any tools for repairing furnaces.
Well, you know, I suspect that that's a hazard of the trade. There's a lot of things that you could run into if you want to do a safety check on a system, like on a boiler, or maybe a bad blow down valve, or
that's probably the kind of thing that inspectors are not going to do. So I guess if they're looking in here, should they look for like crystallized insulation or corrosion, and maybe be recommending an annual service?
Yeah, those might be indications, but moreover, in these types of controls, I'd look for burnt wires.
Okay.
I'd look for insulation that's cracked or looks like it's charred, or some high temperature failure of a system. Mm-hmm. If you go to a limit switch like this and you see the wires are really, or the plastic connector is melted, or wires charred back in here,
brittle,
I'd say you might have had some problem in the past. Maybe it's fixed by now, but I know if I was servicing your furnace and I found that, I would either run a new wire, I'd take that old wire, cut it back to where it's not charred, I'd put a new connector on it, and I'd have a nice brand new system.
So if we see overheated or signs of overheating, that's when we recommend service.
You bet.
One more question here. I see what looks like two fans here. I thought we were just looking at one fan that lowered the pressure in the heat exchanger. So there's a fan inside this housing, the big round housing, and there's another fan here.
Oh, that fan on the outside there is just the auxiliary fan. This is what we call an air over motor. Don't forget, we're dealing with temperatures of 150 to possibly, if there's a failure, 300-400 degrees at this point.
In the heat exchanger?
Well, the heat exchanger will never get to that temperature. At least, hopefully, it won't.
Those are exhaust gas temperatures.
The exhaust gas temperatures could get that high. So this combustion blower motor is bolted right up to this hot heat exchanger. This little fan here is just for cooling for that fan motor, to kind of prolong the life of that system. Mm-hmm. So yeah, it's a single shaft, but a fan blade on each side. This side, of course, has a centrifugal fan or a squirrel cage little blower on it. And this one's just a really low pressure propeller type fan to cool that motor down. That's, I think, the basic rundown on your 85% furnace, then, Ken.
And that's about the same whether it's induced or
forced.
Forced.
Yeah. Control sequences are all the same. The only difference in the actual operation is that this pressure switch, instead of detecting negative pressure in the heat exchanger, it would be detecting positive pressure in the heat exchanger. Some of the older systems years ago too, certainly on the rooftop units and that, the light commercial stuff, rather than a pressure switch on those combustion chambers, they used what we call a centrifugal switch on the inducer motor itself. As that motor started spinning up, it would throw these counterweights out and close the switch on the outside. You could actually experience problems with your system, like a plugged up vent, but the centrifugal switch might still make. So
it'll still be spinning. Yeah.
Pressure switch is a better, safer alternative, and we'll see those on all of the newer systems. One other final aside: these pressure switches, we're dealing with very, very low pressures. Inches water column, maybe a couple of hundredths of an inch of water pressure, water gauge pressure. When we deal with locations at altitude, like Denver location, or certainly if we're going up into the mountains somewhere, we might see very low pressures because the air is so much lighter. A lot of the furnace manufacturers actually have a replacement pressure switch that they put in that they'll ship you for a high altitude location because they have to be a lot more sensitive to the lower pressures that we're experiencing at our altitudes here in Denver and up in the hills up here. So that's one potential failure. But the good part about that is that the failure would be that the furnace won't come on. It won't develop enough pressure to close this switch and enable the gas system. So it won't go the opposite way.
It might go through the purge part of the ignition, but it won't actually ignite.
Right.
Okay.
It'll bring up the combustion blower and everything will go, but we won't ever close this switch, so we won't ever get a gas valve to open.
Right.
So manufacturers, when they first came out with them, and I think they still do, they offer a high altitude conversion, which is basically to change out the module on these pressure switches.
Mm-hmm. Bill, I was inspecting a mid-efficiency furnace like this one time, and where the metal fan housing extended out of the top of the furnace, it went into the base of an exhaust flue, but only partially. It was as though they didn't really align, and the part of the metal fan housing that didn't align, that stuck out past, had a little plate over it. And it was discolored and corroded, and at that time I called it out as a defect, or at least recommended that it be examined by a specialist because it was discolored. That meant heat, and corrosion meant moisture.
Yeah, well, no doubt it was heated from the exhaust gas. But what they do on these things, Kent, is that these combustion blower motors have varying capacities based upon how big the furnace is, how much gas is coming through them, and the manufacturer of the combustion blower motor might have one or two size blowers, but you may have one furnace that's a 60,000 BTU, another that's 120,000 BTU, and you can see that the bigger the burner compartment, the more area you need to bring through it.
Right.
So that combustion blower motor may have been sized for the biggest furnace, but then when they put it in a smaller one, they partially restrict the opening on that combustion blower so that we don't develop overpressurization of that exhaust flue. Don't forget, in many of these cases, that exhaust flue, the chimney, is going up through the roof. It might have a water heater or some other appliance piped into it as well.
Often does.
If you develop too much combustion air and you pressurize that flue, you can tend to blow the exhaust gas from the hot water heater back down out the draft diverter, and you don't get any exhaust from the water heater at the same time that you run in the furnace. So
excessive velocity might cause backdrafting of the water heater.
Yeah, excessive velocity and volume, because volume, of course, is a function of the amount of air moving through whatever size pipe, and so the bigger the pipe, the lower the velocity. But it's the amount of pressure that you're developing in that flue that we're concerned with. So, they don't make an infinite number of sizes. They don't have a combustion blower for a 40,000 and a 60,000 and a 75 and a 100. They probably have one or two sizes, and so the manufacturer of the equipment will restrict that flue based upon how big his burner is in his furnace.
Right. So unless you see discoloration or especially corrosion, not necessary to recommend call it a defect or recommend servicing.
Well, it's probably not a design defect, but it may indicate that furnace has seen an awful lot of life. And if that, for instance, if that restrictor that's in that exhaust port, if that restrictor were to burn out completely, then you could very easily develop an overpressurization of that flue and be driving carbon monoxide back down into the house from the water heater when the furnace is running. So it's a good thing to observe. It's most people probably wouldn't pick up on that, but it's a good thing to observe. And if it looks like if it's at the end of its useful life, it should be noted.
But okay, so you wouldn't necessarily call it a defect unless something looked really bad. It was about to fail.
I wouldn't call it a design defect or necessarily a field installation, but if it was burnt through or something, I'd be concerned about that.
Okay, got it.
Good call.
Well, Bill, it looks like we've got some white deposits around here, and it looks pretty corroded around the flange.
Yeah, Kent, that was a pretty good observation. You'd make a good furnace inspector. This flue connector here is showing quite a bit of corrosion. We can see some white deposits over here. No doubt that's zinc oxide. These types of furnace collars, the flue collar on here is typically connected to the exhaust system or the chimney system by a single wall galvanized metal pipe. And that galvanized metal pipe, you know, if it's in a basement or someplace, it's going to be a little bit cool. And as the exhaust gas rises up out of the furnace, it starts cooling down. A lot of liquid inside that gas will start to condense back out. Probably ran down the inside of the pipe, started taking some of the zinc off the pipe, creating a zinc oxide, which is what this white powdery material is, and has started to corrode the collar on this furnace. And also, you can see inside here quite a bit of corrosion. Looks like there's some more zinc oxide, some mineral salts, and lots of rust.
Flakes, powders. We often see improperly configured exhaust vents that either have inadequate slope or too long, or you know, for one reason or another, the exhaust gases are cooling down and causing excess condensation that runs down and causes problems like this.
Yeah, it's a typical problem. One of the things that we see an awful lot of is the older style furnaces. Certainly these old gravity type furnaces have much bigger flues than the newer induced draft or forced draft furnaces. When you take a gas stream and you move it through a bigger pipe, it slows down the velocity of the exhaust gas. It tends to hold that gas in the pipe longer, and it gives it a longer period for it to condense back down out.
Right.
Whereas if you've got a smaller vent pipe, that gas flows more rapidly out, and before it has a chance to cool down, it's exhausted through the house or through the roof. So that's one big thing that we see when we have older furnaces replaced with these newer ones with much smaller flues. And you'll see that kind of corrosion. Now this one is an older furnace, and but it's showing that corrosion probably just based upon age.
Well, anyway, if an inspector is looking inside the furnace and he sees corrosion at the base of the venting system, it's a good idea to look at the exhaust vent itself and see if there's a problem of some sort.
On older furnaces like this old gravity exhaust or atmospheric burner, one thing an inspector might want to do is just go over to that exhaust pipe and just tap it a couple of times with the back of a screwdriver. See if you can hear that material filtering back down.
Good idea.
Rust coming off the inside of the pipe. You'll know that you've got a potential problem with a corroded flue.
What's the maximum size, maximum diameter pipe, a vent pipe an inspector should see on a medium efficiency furnace?
Well, vent pipes are all based upon the amount of gas that we're running through that furnace. So the bigger the gas burner in BTUs, and typically residential furnace, maybe in a condo, might be 40,000 BTU. In a large 2,500 square foot house, you might have an older furnace at 160 or 170,000 BTU. And there are vent tables that you can go to, either in the National Fuel Gas Code or International Fuel Gas Code or the Gamma codes, and they'll tell you what the minimum sizes for those pipes need to be. But a maximum size or oversized pipe is as big a problem as an undersized pipe, or can be as big a problem as an undersized pipe.
Slows things down, slows gases down. Yeah.
The last thing I wanted to mention, if we have the time here, is on this heat exchanger in this unit. Again, 85% versus the old 65%. The heat exchangers on these units are much flatter, and they bring a serpentine motion so that the gas comes in the bottom and the gas rises through a series of channels back and forth. That has the capability of holding the exhaust gas or the heated gas inside that furnace for a longer period, so that we can get more air exchange, heat exchange from the air over on that heat exchanger. So you'll see a serpentine type heat exchanger on these 80% plus furnaces. Okay. This is our high-end furnace, high-efficiency furnace. And ignore this one for the time being. That's a pulse furnace. The high-end furnace